In the next example problem, we're given that a car is driving along the road, the driver hits the brake, and over some amount of distance that we're not given, the car will decelerate. During this deceleration, the tires spin 75 times around. So the tires make 75 complete revolutions. We're given the initial and final velocity of the car in miles per hour and in meters per second. Because we always want to work in meters per second, we could ignore the miles per hour. We're also given the diameter of the tires as 0.8 meters, but when you work with circular motion problems, it is much more natural to consider the radius of that circle. So 0.8 meters of diameter implies 0.4 meters of radius. Part A asks us to find the angular acceleration of the tires during the car's deceleration. So let's think about what we're given. Alpha is the term we want. So how do we find alpha? Well, we'll need some equation that includes alpha in it. Let's think about what else is given. The tires make 75 complete revolutions. In other words, the tires spin around 75 times. If I think of one complete circle as 2 pi radians and 2 complete circles as 4 pi radians and 4 complete circles as 8 pi radians, well, the angle through which the tires spin will be 2 pi times the number of revolutions. So I could say that the angle through which the tires spin is 2 times pi times 75. So the angle through which the tires spin, delta theta, is going to be 150 pi radians. 75 times 2 pi. Now, you might ask, why didn't I just multiply 150 times pi to get something a little bit bigger than 450 because pi is 3.14? I just don't feel like doing it. That's my answer. So I'm just going to leave it as this, but this is the angle through which the tires spin. Let's think about what we have now and where we're trying to go. We want alpha. We have the angle through which the tires spin. Is there an equation that might be helpful here? And yes, there is. If we look at omega final squared equals omega initial squared plus 2 alpha delta theta, the angle through which the tires spin will be my delta theta. That's 150 pi, a little bit bigger than 450. Alpha is really what we're trying to find, so it needs to be in there. And we have the initial and final angular velocities of the tires. Well, we don't know the initial and final angular velocity of the tires yet, but we know the initial and final velocity of the car. And we can connect the initial and final angular velocity of the tires to the initial and final velocity of the car. And the way we could connect that is through V equals R omega. If I want, I could say the tires are initially spinning around, and a point on the edge of the tires is going to initially be spinning at a speed of 26.4 meters per second. So 26.4 meters per second is equal to the radius of the tire, which is 0.4 meters. And because this is V naught, this will be omega naught. And I find the initial angular velocity of the tires is 66 radians per second. And very similarly, I could say the final velocity of the car was 15.3 meters per second, which is going to be equal to the radius of the tires, 0.4 times omega final. And I put this in a calculator, I find omega final is 38.25 radians per second. Now, you might want to pause for a moment and say, but wait a minute. We talked about rolling, and when a tire is rolling across the road, you imagine that the location where the tire is in contact with the road, that location has a velocity of 0. And when the middle of the tire will have some greater velocity, and the top of the tire will have an even larger velocity. This is essentially what rolling is. We talk about this in one of the lecture videos. So how could we justify that lecture with what we're doing here? Well, here's the way we could think about that. If you think about rolling as an object that is continuously falling over itself, then the location where the tire is physically in contact with the road, here I have the road, here I have the tire. At this location right here, there is a molecule of rubber right in the tire, and that molecule of rubber is in contact with the road. This molecule of rubber will have zero velocity. And a point on the tire right here will have some velocity, and a point on the tire here will have an even larger velocity. And the velocity of different points in the tire looks something like this. However, this is the perspective of velocity as seen by a person who is standing on the side of the road watching the tire roll by. What is the perspective of a person in the car? Maybe the person sticks their head out the window and decides they're going to watch the tire as the tire is spinning around while the car is going through this deceleration. Hopefully it's not the driver. In that case, what would the passenger see? Well, here is the road, here is the tire. Now remember, the passenger is traveling with the car. And so from the passenger's point of view, the point at the center of the tire will have zero velocity. This point will not be moving, it will not be moving towards or away from the passenger at all. This point on the top of the tire is going to be moving with some speed, with some velocity. And this point on the bottom of the tire is going to be moving with some velocity in that direction. According to a person standing on the side of the road, they see one distribution of velocities at different locations in the tire. According to a person moving with the tire, they see a different distribution of velocities across the tire. So from the perspective of a person riding with the car, they can use this formula to find the angular velocity, initial and final, of the tire. Now that we have the initial and final angular velocities of the tire, we have the angle through which the tire rotates, we have enough information to find the angular acceleration of the tire. So we have the final angular velocity of the tire was 38.25 radians per second. We'll square that, equals initial angular velocity of the tire squared plus 2 times alpha times the angle through which the tires rotate during that deceleration, which is 150 pi. I put these numbers in a calculator and I find the angular acceleration of the tires during this deceleration is negative 3.07 radians per second squared. Next part of this problem, we are asked how long will it take the car to come to a complete stop if it continues with this constant angular acceleration. The way I read this problem, I interpret it as asking how long after this moment will it take the car to come to a stop. I feel it is possible that the author intended to ask how long after this moment will it take the car to come to a complete stop. To me, it is a bit unclear, but I'm going to proceed as though the author intends this to be the initial moment. If you ever come across a question like this on an exam and it's not immediately obvious what I'm asking for, by all means reach out to me. So we are going to say the initial moment here, we already know the angular velocity of the tires at the initial moment. That was 66 radians per second. So I could say omega initial is 66 radians per second. And when the car comes to a complete stop, the tires are not spinning at all. So that's like saying the final angular velocity of the tires will be 0 radians per second. And we're asked to find t. I could look at the equations for rotational motion, and I have omega final equals omega initial plus alpha t. So I could just plug these numbers in. Omega final is 0, omega initial is 66, plus negative 3.07 times t. And when I put this in a calculator, I find the time to come to a complete stop from here to somewhere in the future is going to be 24.5 seconds. Part C of this problem asks us to determine how far the car has traveled linearly from its initial moment until it comes to a complete stop. We know the initial and final angular velocities of the tires. We know how long it takes to come to a complete stop and the angular acceleration of the tires. So we can ask, through what angle do the tires rotate during this deceleration? So I could say theta final is equal to theta initial plus omega initial t plus 1/2 alpha t squared. And if I plug numbers in, let us assume at this moment the tires we will declare have not spun at all yet. So theta initial will be 0. Therefore, we're just asking what is theta final. So I could say theta final is going to be 0 plus omega initial t. That would be 66 times 24.5 and times 1/2, negative 3.07 times the time 24.5 squared. And we could put these numbers in a calculator. We find that the angle through which the tires rotate during the deceleration is 696 radians. Let's think about what this result implies. If the tire spins around once, it will spin through an angle of 2 pi radians. Pi is 3.14, so it'll spin through a little bit more than 6 radians. If the tire spins around twice, it'll spin through 2 times 2 pi radians, so a little bit more than 12 radians. If the tire spins through 696 radians, it's going to spin through a lot of angle. It'll spin around many times. Well, how far does the tire travel? That is kind of like asking, can we convert this angular measure into a linear measure? One way you could think about this problem is pretend there is a string wrapped around the tire, and as the car is decelerating, that string is unwinding. In total, it will take 696 radians to completely unwrap that string from being wound around the tire. So what is the arc length? How long is the string wrapped around the tire? For a tire of radius 0.4 meters that spins around through an angle of 696 radians. The relationship between the length of an arc around a circle of radius r is given by L equals r theta. In this example, we are thinking of the arc length as the length of the string that is wrapped around the tire. And as the car rolls along, eventually coming to a stop, that string is unwinding. So the length of the string will be the same as the distance that the car travels, and that will be the same as the arc length. Now, usually we think of arcs as some fraction of a circle, but there is no fundamental reason why that must be. It is possible for something to rotate more than once around. That just will be indicated by the angle theta being greater than 2 pi. And again, there's nothing wrong with that. So I could say the distance that the car travels will be given by this equation. The radius of the tire is 0.4 meter. The angle through which the tire spins is much greater than 2 pi. That just means the tire spins around many times. 696 radians. And when I put this number into a calculator, I get the distance that the car travels is 274 meters, so about a quarter of a kilometer. At this point, we are completely done with the problem. We have answered everything the author is asking us to find. We found in part C that the car will come to a complete stop after it has traveled 274 meters. However, as an instructive example, see if you could solve part C in a different way. If you think of part C as being almost completely a 1D motion problem, then you could say the car initially has a velocity of 26.4 meters per second. When the car comes to a complete stop, it will have a final velocity of 0. We know the amount of time it takes the car to come to a complete stop. See if you could use that information to find the distance that the cars travel. One way you could do that is you could completely remove all the rotational motion from this example and just treat it like a 1D motion problem. Another way you could think about this is see if you could connect the tangential acceleration of a point on the edge of the wheel to the linear acceleration of the car. And the connection between the tangential acceleration of a point on the edge of the wheel and the linear acceleration of the car itself is going to be very similar to the argument we proposed for why we are allowed to use V equals R omega to find the initial and final angular velocity of the car back in part A. When you go through that line of reasoning, you will eventually find that the tangential acceleration of a point on the edge of the wheel is going to be the same as the linear acceleration of the car. And once you have the linear acceleration of the car, you could treat it like a 1D motion problem. And you should find that the distance the car travels is about 274 meters. When I went through this calculation, I got a number that was slightly off from what I found here, but that was due to rounding and, in my opinion, isn't any real difference.